Okay, so what we would have done in class today that was new, if we had been there, are talking about two terms that you will hear a ton in physics. And if you took grade 9, 10 science in French, you may have heard of these. If you took it in English, for some reason it doesn't show up in the curriculum. But the two words are scalars, and vectors. And again, I will give you printed out notes of these, so you can just watch these videos tonight, and then you don't have to write, or today, and you don't have to write the notes off of them. You can if you want, but I will give you other notes. Something that's a scalar is simply something that doesn't need a direction to be described. It's a measurement, okay, of some kind, but it's completely described by having just a size with a unit. It doesn't need a direction. So it's a measurement that does not need direction. Okay? For example, temperature, right? It might be minus 10 degrees. It might be 30 degrees. Okay? It doesn't need a direction. 30 degrees Celsius, minus 10 degrees Celsius, no direction required. Maybe time. Not maybe, time. Time is a scalar. It doesn't need a direction. How long did it take you to get to school today because the roads were so bad? 1 hour. You're not going to say 1 hour east or 1 hour up, right? It's just completely described by its size and its unit. Vectors aren't completely described by their size and their unit. They are also measurements, but besides the size and the unit, it needs a direction. So a measurement that needs a direction. For example, I want you to push a box, okay? And the unit, so you're going to put a force on the box. And I ask you to push the box down the hall, and I say, in the unit for force is newtons. So I might say to you, push the box with a force of 100 newtons. But if I don't tell you what direction, you might go the wrong way down the hall. So I would have to say like 100 newtons east or 100 newtons to the right. Or someone maybe moved in next door and your mother says, could you take this over to the house and give it to them? It's just like 80 meters away. But if she doesn't tell you it's 80 meters right, you might end up taking it to the wrong house and the wrong people get the welcome to the neighborhood thing. So vectors need both a direction and their size. Now, some of you would have heard of vectors because they're hockey sticks. Some of you would have heard of vectors because they're the name of a granola bar. And some of you maybe heard of vectors because it's a cereal. But from this moment on, when you hear the word vector, I want you to think of an arrow. Okay, because that's in physics, that's what a vector is. It's an arrow where the length of the arrow tells us about the size and the direction that it's pointing tells us the direction. So this might be, 120 meters east, whereas this vector, which is shorter, might be 80 meters west. So when we're drawing vectors, the length tells us, like we can compare the length and we can see, oh, the upper one is definitely longer. They're going in opposite directions. Okay, so vectors and scalars. Some examples of vectors would be acceleration, right? Think about going down the street and the light turns red and you might say, oh, you better accelerate in the opposite direction of your motion. In other words, slow down. If the light turns red, you don't want to speed up. You won't want to accelerate in the direction you're moving. It needs to be in the direction opposite motion. Okay, so vectors and scalars. Now what we need to talk about is vectors. Scalars are pretty good. Imagine if I have a person standing here and they can run at a speed of, let's make it 8 meters per second. And I have a person standing here and they can also run at a speed of 8 meters per second. And they are 16 meters apart. So I might say to you, how long will it take them till they meet? And you might be like, oh, they each go 8 meters per second. They should meet in 2 seconds. that would only be true if they were running towards each other. And I didn't tell you the direction. Maybe this buddy is going away. Maybe he's trying to escape, in which case they'll never meet. Okay? So direction becomes important. If we go back to the box in the hallway, what if two of you said, hey, Sister Kay, I can move that big box down. We can move that big box down the hall for you. We have a lot more muscle. And I might say, okay, if each of you push with 50 newtons, it shouldn't be too hard at all. And then I walk away, and one of you pushes with 50 newtons to the right, and the other one of you pushes with 50 newtons to the left, you're going to be there a really long time trying to get this box to move, because common sense should tell you you're just going to be pushing against each other and nothing's going to move. Okay, so when we start putting vectors together, their direction makes a difference. And because the direction makes a difference, we can't just add these. Because when we add 50 and 50 in this scenario, we get 0, because we have to take into account their direction. So when we're adding vectors, there are really 4 cases. And the first 2 for sure, maybe even the third one, are borderline common sense. Case 1 is when they're acting in the same direction. Okay? Acting in the same direction. So we'll go back to those 2 people pushing on the box. So let's make one push with the force of 30 newtons and the other push with a force of 40 newtons. And they're both pushing to the right, or maybe I'll say east. Okay? Without me even telling you anything about how to add vectors together, I'm pretty sure you're all thinking the total would be 70 newtons. And you would be right. When we're adding vectors acting in the same direction, you just add them and keep the direction. But it's a little trickier than that in some cases. When you go to add them, you have to put them head to tail. So the head is the arrowhead, and the tail is the beginning of the vector. So here's my F1, it's 30 newtons east. And here's my F2, it's 40 newtons east. And then what did I get as a result of these 2 guys is a vector that starts where the first one started and ends where the last one ends. This is the resultant, and like you already thought in your head, it's going to be 7 newtons east. The vector that you get as a result of adding other vectors together is called, brilliantly, the resultant. You will often hear it. Okay, it's just the result of them. It always starts where the first one started. So really, I could have drawn it right on top of this. I was just wanting you to see it, but really it would be right along there. So that's when they're acting in the same direction. And when they're acting in the same direction, we say the angle between them is 0 degrees. If you had a protractor and put it here, that would be 0 degrees. So that's case 1. And like I said, you would have known it without me telling you. You would have known it was added them together. The second one is when they're acting in opposite directions. And again, this is also going to be common sense. Okay, because it goes back to the one I did up above. So here's my box. One of you is pushing 40 newtons east, and this time the other one of you is pushing 30 newtons west. And I have absolutely no doubt that you know what the result of this is, because you would just subtract them and take the direction of the bigger one. So the rule when they're in opposite directions, you still have to line them head to tail. So I'll move my F2 down here. And then the resultant starts where the first one started, which is here, and goes to where the last one ended, which is here. When you subtract them, keep the direction of the larger, it'll be 10 newtons east. Okay, so this would be 180 degrees. So this one is subtract and keep the direction of the larger. This one is add and keep the direction. Okay, so that's case 2. Case 3 is equally as common sense, but I'm going to run out of time, and I'm going to need about 3 minutes on the next video. Okay, but case 3 is when they are at right angles to each other, which of course would